We now have a feel for a wave on a string, where we just have a one-dimensional string and we think about its displacement versus time. But what we want to do is waves of the electromagnetic field. Right? We want to do light. So we have to think about something more complicated than a string. We have to think about a field. So if we're going to do the wave equation for a field, we need to have derivatives of the field and how to deal with integrals and derivatives and calculus with a field. You've sort of done some of it with Gauss's law and vector flux, but we have to go a little bit farther to think about the derivatives. Let's start with something very fundamental. The fundamental theorem of calculus. Very exciting topic, the fundamental theorem of calculus. It means a bunch of things. I'm going to give you one equation that sort of tells you the fundamental theorem of calculus, the integral from a to b of f of x dx equals a different function, big F, at b minus big F of a, where if f of x is basically the derivative dx. I'm giving you the big picture. There's 1,000 details about things being integrable and differentiable on the scale of real, plane of real numbers, all that stuff. I'm not giving you all that. Okay, so a real math professor can give you all the corollaries and axioms. This is basically what it is. In fact, I'm going to make it even worse. I'm going to give it to you in words. Okay? What this is trying to tell you is that the integral of a derivative over a region is related to the value at the boundaries. Okay? So you first see this when you do simple single variable calculus, one-dimensional calculus. But I'm going to try to show you that this applies when you go into fields. So let's remember this basic idea. The integral of a derivative, this is actually the derivative of big F, the integral of a derivative over a region a to b is related to the value at the boundaries, the value of the big function b minus the big function a. So in 1D, this is fairly simple. You can think of it as walking. Okay? Let's say we're walking and F is our position versus time. And we're walking, we go really fast, get excited, let's slow down like that. And we're going to go from A to B as we walk along. Right? We're walking along. And all this is really saying is, if we add up all of our steps, we get the total distance we went. That's really all it's saying. Because it's saying, all we got to do is add up all of our little steps. Well, F in this case is the rate, is the speed at which we're walking. So we take the speed we're going times little time intervals, that's giving us little df's, right? So it's just saying, in this little bit of time, we took this little step, and the next minute we took that step, and the next second we took that step, and if you add up all the steps, you get the total distance from A to B. That's all it's saying. The integral of a derivative over a region is related to the values at the boundaries. So let's apply that to fields and see what happens. To get started, we need a derivative. We need to be able to take a derivative of a field. So let's consider a scalar field. A scalar field, and I'll call it S of x and y. Lowercase s, because I don't want it to get too cocky. Okay, so let's think then if we had sort of an x, y in the plane of the board, and we're going to plot the scalar field S as sort of a height, we could have kind of a lump, kind of like that, and I'll kind of put a line like this. You can get kind of the feel that sort of a lump spreading out in space, in x and y, and we're plotting S. Okay, there's your scalar field plotted as a height. So the question is, what is the derivative? Right? And well, derivatives we know, at least at this point, we know a derivative is a slope. If we just had a line, a single 1D plot, the derivative at any point is just a slope. So you could kind of imagine this thing is flat here and then it goes up. So you could say, well, the derivative here, the slope here, must be small, and the slope here must be big. Right? So the derivative, it depends on position. We have to do something. But that's not too surprising because we have a function, we have a scalar that depends on position. Its value depends on position. And even in a 1D derivative, it depends on where you are. Right? So that's not so bad. But there's something else that it depends on. Let's look here. So this is what's coming down. Is the slope, it depends on direction. It depends on which way you go. If I go downhill here, then I have a big slope. Let's see, I have a negative slope. Right? If I'm coming down the hill, what if I go up the hill? I could go either way, right? I have a positive slope. What if I go around the hill? What if I go around like that? Around this hump? Then it's 0. So not only does it depend on position, it depends on direction. So you actually have the case that your derivative of this 2D scalar field is a vector field. Anywhere you go, it has it has a vector, but you have to think in terms of a vector. It depends, the value depends on the direction you're looking. So we need a way to calculate this thing. We want to know, I don't care about direction, what is the total differential? What is ds? How much does ds change? And we got to think about when I make a move. When I move this way or that way or whatever way you want to go. How do we figure it out? What you do is you say it's equal to the partial derivative, which you remember we talked about partial derivatives. You take the derivative of the function, just considering with respect to x, and you hold y and z if there's a z constant. So take the partial ds dx times the move you made in dx. Okay, so if I want to know what's the derivative this way, I move a little bit in x and I move a little bit in y. And say that's the way I'm going. Well, to get it, it's the partial ds dx times that d differential dx plus the partial ds dy times the differential dy. So if you take a look at it, you could imagine, what if you made this dx be a motion of just a unit of 1 in x, and this be a motion a unit of y and y? You could think of that as sort of like the unit vectors. So let's look at a way that we could write this. What we could say is to find this, we need to use something that looks like this. D dx I hat plus d dy j hat plus d dz k hat if we had a 3-dimensional function. Right now we just have 2, so you can ignore this, but I'm trying to be general for Cartesian coordinates. This thing is what we call del. This is the differential operator for fields. It doesn't really multiply fields, it just operates on fields. It's like taking a derivative of a function. You don't multiply the function times the derivative, you just take a derivative. So when you apply del to a field, you're not multiplying by the field, you're just taking the del of a field. So for example, if we have the scalar field S, then del S is ds dx I hat plus ds dy j hat plus ds, in this case we're doing all 3 dimensions, dz k hat, like that. And this is the gradient of the field. Because like we just showed, if you imagine you're going in some unit direction, in these different directions, multiplying by ds dx gets you the change, the little bit of the change in one direction, a little bit of the change in the other, a little bit of the change in the other. If instead of thinking of a differential in a specific direction, if you just do this to the field, what it gives you is a vector pointing along the maximum change. And its magnitude of that vector is equal to the maximum change. So if we came back down to our drawing like this, it's true that in all these different directions you can come up with different ds's as you move in different directions. But if you take the gradient, you just get the maximum change straight up. It'll give you the direction and the magnitude. That's what the gradient does. So the gradient is one of the ways to take a derivative of a field. It's the way, applying it this way, just taking the gradient, applying it directly to a scalar field gives you basically the three-dimensional version of the derivative you're used to. It gives you the three-dimensional gradient of the field. Now, let's apply the FTOC, the fundamental theorem of calculus, to come up with the fundamental theorem of the gradient. Fundamental theorem of the gradient. What does that mean? Well, let me draw my humpy field here again. So here's kind of a hump like that. And let's let it go down into sort of a hole, into black, into just nothingness like here. Oh my goodness. Let's see, that totally works for you, I'm sure. Let's see, like that. Who needs graphics? Okay, so let's imagine then we have sort of a field like that, where again, we're plotting S as the height as we move around. Okay. All right, so the fundamental theorem of the gradient. Well, what do we say? It's that the integral of a derivative over a region is related to the values at the boundary. Okay, so what we're going to do is say the integral of a derivative, the gradient of the scalar function. In this case, the region will be 2 points. We're going to walk from A to B. Say we're going to go into this hole down here. We're going to walk along this scalar field. So the A to B like that. And if we're going to walk, we have to think of little dLs as we walk. It's a contour integral or a path integral. Because remember, the gradient gives you a vector, so it's dot dl. Okay. The integral of a derivative over a region, that's what we have there, is related to the values at the boundary. So that equals SB minus SA. This will just give you literally the difference between the height, the scalar height here, and the scalar height here. Okay. So that really doesn't have a name. That's just the gradient. That's what everybody thinks of as the gradient. And of course, the gradient does that. It's a fundamental theorem of calculus. But I'm going to go through all the field derivatives and name them each as a fundamental theorem of calculus. So this is the fundamental theorem of the gradient. I made that name up. Don't go say that name anywhere. This already looks a little bit like some physics that you know, doesn't it? Let's see. If we were to exchange the scalar field for the potential, if we had VB and VA, if that were the potential at 2 points, and say this were a potential surface, so you had a positive charge here and a negative charge down here, how would you get the potential difference? We did the integral of E dot dl, right? We had to walk along and add up the E. We were thinking about if you were pushing a charge, so you'd be moving around E dot dl. Well, that would be del of V. And that's the same thing we talked about, how the electric field is the derivative of the potential. Well, and this is just a three-dimensional case. If you have a three-dimensionally varying potential, the electric field is the gradient of that potential. There's a negative sign in there for reasons that we talked about before. But this already kind of looks like something you've seen in electrostatics. Let's move on to another derivative. We have our way to take derivatives now. Del d dx I hat plus d dy j hat plus d dz k hat. And we applied it to a scalar field. Now let's apply it to a vector field, which I'll write just big V. And a vector field, we've dealt with many fields, vector fields by now, electric fields and magnetic fields. If you're going to write one really general, you write it like this: Vx I hat plus Vy j hat plus Vz k hat. And these are not constants. Vx, Vy, Vz aren't constants. They're not even just functions of x, y, and z. They're any function. So Vx, Vy, Vz are some function of x, y, and z. They could be constants. They could be anything. The point is, these are really functions here, even though I'm calling them Vx, Vy, Vz. So we want to have our operator operate on a vector field. So how is it going to do that? Well, we said they're not really multiplying. They're really operating on, but they operate on things in a way that looks like multiplication. So if this thing kind of looks like a vector and this looks like a vector, how are you going to combine them? Well, one way is a dot product. So what we can write is del dotted with v. Okay, it looks kind of the same. V was an unfortunate choice. So that's a del, and this is a v with a vector sign on top of it. Okay, if you do that, d dx operates on vx. So that's d vx dx, and d dy operates on vy, d vy dy, and d dz operates on vz. So that's your dot product. And again, keep in mind, these are functions. Vx, vy, vz can be functions of x, y, or z. So if we do this, it's called, it gives you a scalar field, first of all. Dot products always make scalars, and these make scalar fields. So this is some function x, y, z, function x, y, z, function x, y, z. Add them together, it's a great big function of x, y, and z. It's a scalar field. And it's called the divergence. Is the name of this derivative. You take vector field, take its dot product, or take del dot with that vector field, and you get the divergence. Let's look at one and see why it's called divergence. Let's actually just make a field. V, let's call it x I hat plus y j hat. Okay. Now I said you could have a function of x, y, and z here, and you can. It can be very complicated, but I'm actually going to draw this, so I would rather not make it too complicated. Let's see, if I were to draw x and y axis like this, then at x equals 0, y equals 0, you'll have nothing, 0, 0. But if you start to move away, say you move away in x, you move to x equals 1, y equals 0 here, now you'd have a vector with a value of 1 pointing in the I hat direction. It'll look kind of like that. And if you moved up 1 in y, it would just point up in y. And if you moved down 1 in y, it'd be negative. If you moved down 1, negative 1 in x, it'd kind of look like that. And if you went to 1, 1, you would be what? You'd be kind of like that. And 1, 1 here would be like that, and like that, and like that. It kind of looks like the field around a point charge, but it is not. Okay, so field around a point charge is spherical symmetry. This is actually sort of a Cartesian thing we're making. If you move out to 2, here, now it's twice as long, and this one would be twice as long, and this one would be much longer. So this field kind of looks like the vectors are just exploding out of the origin, if I were to describe it kind of like that. And if you go further away, they get even bigger, like this. And if we kept doing these, but really we need to fill in all the Cartesian points if we wanted to completely draw it. Okay? So you get the idea. The field is blowing out of the board. Okay? So let's think, what is the divergence of this field? Well, del dot v is d dx of x is 1. Right? All right. d dy of y is 1. I just took the derivative of y, and I got 1. And we're not doing z. So the divergence of this field is 2. It has a divergence of 2. So the way to think of it is diverging is just to drop a little cube on it, say, like this. A little three-dimensional cube. And just think about how much field is going in and how much field is coming out. So right here, you have small vectors going in, you have big vectors coming out. You get a positive number if you do the number coming out minus the number coming in. That's because the field has divergence there. Okay? If you put the box way out here, now anywhere you go, smaller fields are going in that are coming out. That's because the field has a constant divergence. Its divergence everywhere is 2. If you go on an axis right here, a little bit of field goes in, a larger field comes out. Okay? The field is diverging. If you go right on the origin, you can go on the origin, all it is field coming out, right? Because all the vectors are pointing out. So divergence, the property divergence is like creation of field. We could contrast it with a uniform field. So if I were to, over here, just let me draw a uniform field equals 1, now I'll be more interesting, 2 I hat, okay, plus 0j plus 0k, I, x, so I made just vectors like this. this is the generic uniform field that we've drawn many times in electricity and magnetism. Its divergence is what? Del dot V is 0. This thing has no divergence because the derivative of that with respect to x, that's just a constant 2, 0, 0, 0. And if you draw these cubes, you see a uniform field, the amount of field going in equals the amount of field coming out. So also there's no field created inside the cube. So that also matches the idea that the divergence is 0. We have a new derivative, so fundamental theorem of calculus, the fundamental theorem of the divergence. Or, to those of you who are in the know, it's called the divergence theorem. If you want to sound fancy, you can say the fundamental theorem of the divergence. So we remember the deal. The sum of a derivative in a region, or the integral of a derivative in a region. So let's see. We're going to take the integral of our derivative, del dotted with v, that's our divergence. And it's sort of it's a scalar. So it's something you have to fill a volume. We have to think about a volume for this one. So the region, in this case, is a volume integral. So this scalar, del dot v, times just dv, okay, doing a volume integral, is related to the values of that field at the boundary. So if we're doing sort of a volume integral, we're thinking about the divergence inside. The boundary is a surface integral. So we want to go the integral around the closed surface. So if this is some volume, any volume has a surface all the way around it. So it's a closed surface integral of just the field. And since it's the first surface integral, it has to be dA. Okay? The integral of a derivative in a region is related to the values at the boundary. Same as the other two, just written for different dimensions and different kinds of derivatives. And it sort of matches what we were talking about. If a field had divergence, right, if it looked like field was being created in the region, then we said it had to have a net amount of flux coming out of a cube. Well, of course, that's the vector flux. That's what we've been talking about with the electric field. This looks a lot like E dot dA. So you can see where all this is headed. The divergence theorem looks a lot like it's useful for Gauss's law, right? This looks just like Gauss's law if you put an E field there. So let's do that. Let's apply the divergence theorem to Gauss's law. Okay, well, all we got to do is switch V to E, right? So we could say, we already know this is Gauss's law. If we go around a surface and we have E dot dA, well, we know that is what? We know that's Q enclosed over epsilon naught. Okay. What we need to do now is think about Q enclosed. So rather than think about a point charge, if we're doing fields, we can think about a uniformly or just a charge density in space, rho. Right? So rho is our volume or three-dimensional charge density. So if you just think of rho as a function, then this becomes the integral of adding up all the rho, dv, and we're over epsilon naught. Okay. So any volume, if you do integral of rho dv, if it's a point charge or whatever it is, you can figure out all the charge enclosed. Let's see, and this would be, yes, this is the volume integral of this same region. But then at the same time, we can apply the divergence theorem to the E field and say this is equal to integral of E dot dA on the surface is equal to the volume integral of del dot E dV equals the integral of the volume of del dot E dV. Okay? And then this is where you get the differential form of one of Maxwell's equations. You see that the thing inside the integral is the same, right? This is a volume integral of rho over epsilon naught dV. This is a volume integral of del dot E dV. So these two parts in this volume are the same, and this is what gives us then the first differential form we've got. del dot E equals rho over epsilon naught. So here, using fundamental theorem of calculus, I've showed you that this is the same Gauss's law as what you're used to. And now we'll look and see when to use which one.